So let me summarize the result. Result is that we have an SU gauge theory with one complex scalar in representation Rs and one Dirac fermion in representation Rf. And then we discovered that the coupling constant, one loop coupling constant, is the coupling constant of the classical theory 1 by g square minus 1 by 48 pi square 1 minus 12 CV plus the C of scalar field contribution corresponding representation Rs of the scalar field plus 4 times the C of Rf coming from the fermion contribution. So this is what our final answer is, times log q square. So first thing to notice is that from the fluctuations of gauge field, small a fluctuations, we got an answer 1 unit here, and due to the non-abelian nature of the theory, we got an additional contribution of minus 12. That's why I've written them separately. And for a complex scalar field, which is 2 degrees of freedom, we got the same answer, 1 unit. This is gauge field is also 2 degrees of freedom for every the internal index A. So this counts in some sense the how many internal indices you have. It is the trace of the corresponding charge matrices T A T B. This is the charge of corresponding charge of trace of the charge of T A T B for the scalar field theory. 1 unit for complex scalars. A Dirac fermion is made up of 4 complex objects. So therefore you have the same answer with 4 units here. There are 4 degrees of freedom in Dirac fermion. Electron, spin up, spin down, positron, spin up, spin down. So this number 4 is that. Clear? And all of them contribute with the same sign. But it's this non-abelian nature of the theory which is contributing with a negative sign. Clear? If you didn't have a non-abelian nature, then this all would be a positive object. That's what happens in QED. QED, you have the corresponding numbers here, you have the corresponding charges here instead of these objects. For scalar field, scalar charge. For fermion, 1 unit of charge. So the asymptotic freedom is not in an abelian theory is clear from here, and it's there in the non-abelian theory because this object can beat over this and change the sign of this term. So from here let me write down the what we call beta function. All right, before that, now instead of one scalar field and if I have more scalar fields and more fermions. So let me say for ns scalar fields, complex scalar fields, in representation Rs, they could be different representations, but let me take them to the same representation. And nf fermions in representation Rf, this answer would be clear? And if they were in different representations, then you would have the corresponding C's multiplying those. And the beta function was defined as beta of g as twice derivative of g with respect to derivative of log q or log q square. And from there you can work it out what it is. It's minus g cube of q by same 48, I think 48 pi square 11 CV minus NS CS CRS minus NF CRF. And for sufficiently small number of these objects, when this thing beats over this is negative. And then you have asymptotic freedom. But if you increase the number of scalars and fermions in your theory, then you can change the sign of beta function. 4, yes, factor 4, very important. Clear? I could also write g square of q as g square 0 plus beta of g divided by gq log q square. Just use this in here. I have the sign right. I think I have the sign wrong, right? Beta is negative, but I have this order is changed, right? So that is plus with that sign, so this should have been negative, right? I think I have sign error in my notes. Yes, I think I have sign error in my notes. All right. Now, I want you to do the following thing. This is homework. One homework is write neatly what we did earlier, which means contribution of scalar and fermions. We have done it already in the class, and we've done discussion. Contribution of a complex of a complex scalar fields, ns scalar fields in representation are S and NF Dirac fields, Dirac fermions in RF representation. The same thing, just write it down cleanly on a sheet of paper and submit it. I won't see how well you have understood the steps. Second exercise. Calculate the beta function for an SU N-gauge theory with 3 complex scalar fields in adjoint representation, all of them in adjoint representation, 3 complex scalar fields and 2 Dirac fermions again in adjoint representation. Can anybody tell me what is the answer quickly, even without having to write it down? You have the answer here. Anyway, so it's a simple exercise. This is one loop beta function. So one loop beta function. One loop. Three, count the number of physical bosonic degrees of freedom and fermionic degrees of freedom in this theory. Yes, everything in adjoint. Yes. Both scalar fields in adjoint and complex and Dirac fermions in adjoint. 2 Dirac fermions, 3 complex scalar. And count the physical degrees of freedom. Physical degrees of freedom means not gauge degrees of freedom. Gauge field has 2 physical degrees of freedom, 2 polarizations, so you count 2. Same, how many degrees of freedom does scalar field have, and how many degrees of freedom does Dirac fermion have, physical degrees of freedom? There's a nice property there, hiding. Very obvious to read. Notice that. And if you have understood it, then you would have calculated one loop beta function for what is known as n equal to 4 supersymmetric Yang-Mills theory. It was not an easy property to discover it took many years for people to discover this simple property of n equal to 4 Yang-Mills theory. Of course, in the way we set up this theory, this is not those properties of beta function, whatever nice answer you will get here, is not true to all loops. It's true only to one loop. Second loop, that's not true. The answer will be different. But if you do some more massaging to it, put more structure to it, then you can ensure that the same answer is true for all loops. And that massaging is setting up the complete n equal to 4 supersymmetric Yang-Mills theory. So now let me, from here, go on to, so let me use here. And these homeworks by Monday, because you've already done everything. Give it to him. Now let's discuss a more physical theory. QCD. QCD is the theory of strong interactions, quantum chromodynamics. That's what QCD stands for. It's an SU 3-gauge theory with a set of fermions in triplet representation. Dirac fermions, set of Dirac fermions. So these are the fermions that we see in nature. They are given names. You have already perhaps done a course on particle physics. There are 6 of them given names: up quark, down quark, charm quark, strange quark, top quark, bottom quark. There are 6 of them. They are in the triplet representation of SU3 dynamics here. And this dynamics controls the strong interaction properties. So now that we have a general formula for the beta function of this theory, we can write now the beta function of this theory: G cube Q over 48 pi square 11 times CV. And CV for SU1 theory, we had said, is so this is 33. Then it has a set of fermions. And in the triplet representation, and in triplet representation, C of triplet representation, can anybody tell me what it is? For SUN, we had said that we have matrices. If we write down in terms of n cross n matrices, TAs, that's what we said about theory in the beginning with. We put trace of TA triplet or n-dimensional, let me call it n, n dimension for SUN. was, and that's what this number is. This is the same number for our SUN theories. For SU3 theories, it's half. And therefore, we have this answer here. So this is the beta function for QCD. And like I said, NF for QCD is 6, because we have up quark, down quark, charm quark, strange quark, top quark, bottom quark. Each one of them is in a color triplet. So therefore, this number is so the QCD is an asymptotically free theory, in sense that the coupling constant as a function of momentum decreases as the momentum increases. Beta function gives you the rate of decrease. From this formula, asymptotic freedom has an upper bound for the number of fermions. Because if I have fermions NF to be 16, that is still 32, that is smaller than this, so it is negative. But if I have more than 16 here, then it will change sign. So if in nature I had more than 16 fermions, colored fermions, then I would not have asymptotic freedom. Up to 16 fermions, I can have it asymptotic freedom. But so far we know there are only 6 of them. So we are, as we know the QCD, that is asymptotically free. But for some reason, if we discover more quarks, we still can go up to 16 in order to retain this property. Now we did this calculation in Euclidean theory, but the real world is Minkowskian. And I said that, I justified earlier that whatever answers we get in Euclidean theory have to be right also in Minkowskian theory, because of the analytic continuation I could do in momentum integrations. So let me rewrite now, because QCD is a real theory, answers in real world. What do I mean by doing that? We had Q square momentum Euclidean. This was defined as the 4th component square plus, this is what a Euclidean Q square is. But this object, if I want to write it in terms of Minkowskian momentum, this object is I times Q0. So square of that is minus. So this is minus square. And then, so this is Euclidean, this is Minkowskian. And this is Q square Minkowskian. with the Minkowski metric now, square here with the Minkowski metric, which has signature +1, -1, -1. And let's call this object some plus q square m. Define alpha SQ to be g square q by 4 pi. G square is the coupling constant that we introduced there, divided by 4 pi. And you must have noticed that everything comes generally in this combination. And this is really the effective coupling of the theory, g square by 4 pi. In the same way, find structure constant in electromagnetism, E square by 4 pi. In the units, h cross c equal is h cross 1, c cross 1, c 1. So this is the real coupling constant, like the fine structure constant of electromagnetism, of strong interactions. That's why it's S here. So from what we have learned earlier, alpha s of momentum q prime is related to alpha s of momentum q by, I've given a name now, this is b0 by 4 pi log q prime square by q square, where b0 is 33 minus 2 nf by 3. 3 or? Yeah. From there, that formula only. This is the coefficient of beta function, so b0. So the QCD coupling constant at two different values of 4 momentum is related at one loop this relation. In particular, this is true. Did I have the signs right? Signs are wrong, huh? Minus. They should be minus. They should be minus. Yes. So which means that this combination is momentum independent. And let me give a name to that combination now, which is momentum dependent some constant. Well, let me not call that lambda, but call some constant. And let me do one thing, divide this by lambda square. Divide this by lambda square. But that's just adding constants to both sides. Clear? And now let me make a choice. What lambda is an arbitrary number, right? Some arbitrary constant. Let me make a choice. Which means take lambda such that this constant is 0. Lambda is arbitrary constant, so I can always do that. Then or alpha SQ is 4 pi by B0 log Q square over lambda square. So what does it mean? This means that coupling constant of QCD for large Q behaves like inverse of logarithm of Q square. Is that very clear? Huh? Large compared to lambda now. Right? So there is some scale lambda now we have introduced as compared to some scale lambda when Q is of the order of lambda. Log 1 is alpha is large. So which means QCD becomes strongly interacting when momentum transfer Q is of the order of lambda. But if it is much larger than lambda, then coupling constant of QCD is small. And it is small like 1 by log of Q square. These are experimental properties that have been observed. In fact, this is what is called scaling properties. For large Q, the coupling constant was observed to have a scaling property. And it was to explain that scaling property, then QCD somehow became the theory of strong interaction. But now lambda is an arbitrary parameter we have put in. We don't know at what scale QCD can become strong. Some scale. Now that observation is also experimental, which is quarks live inside baryons, a proton. When quarks start feeling the full size of the baryon, which is large, baryon has a size, proton has a size. When they start feeling that size, which means the momentum, when large distances are felt, then momentum becomes small. But since we know that you cannot have a free quark, then the interactions have to be strong, which means a lambda essentially is qualitatively controlled by the size of proton. Is it clear? So inverse, this is momentum, lambda is in momentum, so lambda is related to the inverse length size of proton. So that's a physical object. So lambda, this is lambda QCD. Lambda QCD is a physical object quantity. Theory does not fix it for you, at least so far. Maybe some non-perturbative properties of theory may do it, but perturbative properties of QCD don't fix what lambda is. It's the experiment that fixes what lambda is, which is essentially the proton size. Now, a careful experimental analysis of E plus E minus interactions, you hit electrons and positrons and create quarks and anti-quarks, which means create hadrons. When you study these kinds of processes experimentally, give you a value for lambda which is of the order of 200 MeV. So now if this object is 200 MeV, lambda or lambda square is lambda is 200 MeV. Perturbation theory QCD would be true if alpha QX is small. You can use perturbation theory only if the coupling constant is small. So now if alpha Q has to be small and lambda is this much, that puts a certain upper value for a lower value for Q square, up to which you can study the properties of quarks perturbatively. Say for example, if I was doing an experiment where Q square was 1 GeV, 1 GeV square. No, well, Q is 1 GeV. Q is 1 GeV is that means 200 divided by 1 GeV is 1000 MeV. So that's 1 by 5. Then Q square by lambda is log Q square by lambda is 2 by log 5 by 200 is 5. That would tell me alpha SQ is 4 pi B naught 2 log 5, and B naught is 33 minus 2 NF by 3, and NF is 6. So, so this is how much? 12. 12 is, this is 21 by 3. That's about 7. That's 7. So let me put here. So it is 2 pi by 7 log 5. Now you can just work it out what numerically it is. 2 pi essentially is 9 and log 5 it is. This object is of the order of 0.4. So if I am doing physics at 1 GeV, these interactions that take place here, they exchange a momentum of the order of 1 TeV. 1 GeV. Then I can study the properties of these quarks, the strong interaction properties of these quarks, because the coupling is only 0.4. Okay, is that clear? That's a little bit of physics. I have another 15 minutes. I want to discuss some other property of this theory now. What I want to discuss is something called scale invariance. So let me go back to my Euclidean SUN theory, Euclidean SUN gauge theory. Action is given by 1 by 2 G square D4x F mu nu A x F mu nu A x. Euclidean and Minkowski doesn't make any difference, but we are doing Euclidean, so keep those conventions for this discussion. So let me not add matter to it, but if you add matter to it, massless matter to it, the properties I'm going to describe are going to be valid. But let's analyze only pure Yang-Mills theory. Scaling transformation. Let me transform x by some lambda x. Every coordinate x, the 4 coordinates x1, x2, x3, x4 have. Let me scale them by amount lambda. Lambda is a constant. And if I scale distances by lambda, I scale momentum by lambda inverse. So momentum I scale mass by inverse, because we are working in C equal to 1 units. Mass is energy, energy is momentum in dimensions. What are the mass dimension of gauge field? Can anybody tell me what are the dimensions of mass dimensions of gauge field? 1. Is that clear? Because that's how in H cross equal to 1, C equal to 1, action is a dimensionless object. But if you have H cross also, then you put H cross, S by H cross, that is a dimensionless object. This is length dimension 4, F square has to be length dimension minus 4 or mass dimension 4. Derivative is length dimension mass 1 inverse, so A has to be length dimension minus 1 or mass dimension 1. Is it clear? And from here also, since x scales like lambda x, derivative scales as lambda inverse. From there, here, these two properties, f mu nu a x scales like and f mu nu a square that is the object we have here. So this object scales by lambda minus 4 and x scales by this, therefore d4x scales by lambda to the 4 d4x. So S goes to S. S is scale invariant. Clear? So pure Yang-Mills theory, pure electromagnetism, or Yang-Mills theory, is scale invariant, classically scale invariant. This is all classical, we're doing classical thing. Is classically I could write this action also in momentum space that we have learned how to do it. I thought, I think this is, 2 or 4? Huh? 4, I think. When we put trace, then it's 2, right? It's 4. This action in momentum space is this object. A mu x in terms of its Fourier transform is this object. Now, if Ax scales like this, its Fourier transform scales like is that right? Or lambda inverse. So this is lambda 4 or 5, right? Is that correct? Cube or 5? I have somewhere written cube, I think. Oh, lambda here. No, sir. What did I do? Wait, let me see. This is what it is. Yes, so this goes as lambda here. Yes. Is that clear? This scales as lambda inverse, this scales as lambda to the 4, so this, therefore this combination scales as lambda to 3. And similarly, this object scales. The momentum transform of F scales as lambda square. Same thing, like this scales as lambda to the minus 2, the Fourier transform will scale lambda to the 4 times lambda to the minus 2, so that is lambda square. Yes. Yeah, maybe I should write it without the arguments. You're right, without the arguments. Here also I should write it without the arguments. So from here, this is lambda square, lambda to the 4, and q goes by lambda to minus. So this is again scale invariant. So whether you look at it from that point of view or from this point of view. So S is classically scale invariant. Now let's see what happens to quantum theory. And since we have evaluated one loop, let's study one loop quantum theory. We've done perturbation. The action from classical changes to the one loop effective action. And how does it change? Well, let me here g square of q. And g square of q is g0 square plus beta of g minus beta of g by g cube log q square. Now, this times this we have seen already is invariant under scale change. But earlier coupling was independent of Q. But now quantum coupling depends on Q, and Q changes under scale. So scale transformation. Because Q changes as lambda inverse Q. So what have we discovered? We have discovered that S effective under scale transformation change is S effective plus 1 by 4 d4q 1 by 4 log lambda, and maybe factor of 2 here, and this 2 pi 4 beta of g. Something is not right. Something is not right. This should have been g cube, right? And what we have discovered is that in quantum theory, S effective is not invariant. Though classical theory has scale invariance, quantum effects break scale invariance. Clear? And this scale invariance is completely characterized. This non-scale invariance or scale non-invariance is completely characterized by the beta function by g square, g cube. So this is a interesting but somehow strange property, is that you have a theory which has a classical invariance, but a quantum theory you lose that invariance. So this is an example of what are called anomalous invariances. This is an example of anomalous invariance. By anomalous, what we mean is that classically you have the invariance, quantum theory does not respect it. This is not the only such theory. There are other examples, invariances. There are other invariances also. There are other examples also. Examples of such anomalies. But if I have somehow a theory where beta function is 0, then such a theory would be scale invariant even got quantum. So a theory for which beta function is 0 scale invariant even at quantum level. And yes, yes, it's true. Now it should be beta function to all loops must vanish. Then you will have invariance even at the quantum level. But if it vanishes at one loop level, that is not good enough. That means that some other quantum effects will break it. So you have already had a glimpse of one such theory, which is your exercise, where you will discover that beta function is 0, at least one loop 0, and then therefore at least one loop scale invariance is valid even in quantum theory. Okay, I think we'll stop here. Now, do you have any preference what you want to do now? Means this this aspect is now closed. Now I want to shift to another topic. Huh? Do you want to do some non-perturbative field theory, or do you want to do some supersymmetry? Theory of weak interaction. But that is the theory of weak interaction is a field theory of this kind with some. But that standard model you have done somewhere, right? You want to redo that? Huh? Higgs mechanism. Spontaneous breaking. Okay?